Today we're going to look at domain and intercepts of rational functions. This part clearly should not be new to you. Finding these things for rational functions, even though it may not be new, probably haven't done it a whole heck of a lot. So there are few little things that we have to pay a little bit closer attention to. Okay, so first we're going to revisit slant asymptotes, because I told you last time that I would explain to you this whole remainder thing. So remember that another word for slant asymptotes, think about what that is. It's oblique. Okay, you could see either word. So what we're going to do is go ahead and factor so we can find what we need to find for this. So if I factor this function, f of x, it's going to equal, see, I'll have x plus 2 in the denominator. In the numerator, I'm going to have x, and this is going to be minus 1 and minus 3. Okay. So with that, let's think about the things that we would need to find. So do I have any point discontinuity? I don't have anything that I can reduce out, so the answer to that is no. So that is none. Vertical asymptotes, get that from here. It's the zeros of the denominator, so that means that this is going to be x equals negative 2. Remember, it's always an equation of a line. Horizontal asymptotes. So let's think about what it means when they're top-heavy, bottom-heavy, and tied in degree. Okay, so if it is top-heavy, then it doesn't have a horizontal asymptote. That is none. If it does not have a horizontal asymptote, then it might have a slant asymptote, not always, but this is a second degree in the numerator, first degree in the denominator, so I will have a slant asymptote. To find that, I need to actually divide, and I would use this form to divide. So I'm going to use synthetic division. Inside is going to be 1, negative 4, and 3. Put a little place for my remainder. This is 1, negative 2, negative 6, 12, and 15. Okay, so that means that my slant asymptote comes just from this part right here, so this will be y equals x minus 6. All right, so let's talk about this. We ignore that to write our slant asymptote, but let's think about what's really happening here. What I did to get that, right, to get to this, or to divide this out, I actually divided this. So this, I'm going to put it over here. This whole thing, including the remainder, is another version of this right here. So f of x is equal to x minus 6 plus the remainder, which is 15 over x plus 2. So I want you to think about that for just a second. When I have this part plus the remainder, that's actually the exact same function as this. It's just in a different form, because I divided it out, and this is what it's telling me to do, and I include the remainder. So if I include the remainder, when I'm talking about my asymptote, I'm not going to get a line. I'm actually going to get the exact same function as the original. All right, so that still doesn't tell me what the slant asymptote does. So the remainder, just the remainder, is 15 over x plus 2. All right? So the y equals x minus 6 is this dotted line right here. So we have a vertical asymptote. We already knew that. That's x equals negative 2. And then we have this slant asymptote that's y equals x minus 6. Remember, if I actually put this part on it, I'd get a rational function. I wouldn't get a line. So just like any other asymptote, let me enlarge this a little bit. The function is approaching the asymptote, right? So down here, this is the distance from the function to the asymptote, all the way. And so it's getting closer and closer and closer and closer, right, as it goes. It'll never actually, well, it might cross it and come back, but again, when we're talking in behavior, it would still be approaching and it wouldn't be like right on top of it. So what this number is right here, this is the distance this function is from the asymptote. So if I substitute in, let's see, what are we counting by? Okay, so we're counting by 4s. So if I substitute in a 4 here, right, I get this point is when x is equal to 4 because we're counting by 4s on here. So I'll get 15 over 6. That's this distance right here. If I substitute in an 8, I'd get 15 over 10. Then, of course, I'd reduce it. That's just this distance here. So the bigger and bigger x gets, as x approaches infinity, f of x is actually approaching that line, and the distance it is from that line is this number right here. Okay. So, whoops. What this is the distance. The function is from the slant asymptote. So that's just a little FYI, so you don't think it's just random that we ignore it. It actually does mean something. We're not really going to use it or do anything with it right now, but I just wanted to make sure you knew what was going on. Okay, so let's talk about the domain and the intercepts and so forth. Okay, so to find the domain, this is important. We do this first. Okay, we do this. It's the first step before reducing. So not really, the very first step is going to be factoring, but the first thing that we find then is going to be the domain. You have to do that before reducing, but because those holes that we find when we reduce, they affect the domain, so this is important. Then to find our zeros, that happens after reducing. That means if I'm going to do it after reducing, that is after finding our holes, which are point discontinuity. And the way we find the zeros is that we actually find the zeros of the numerator. It's the zeros of the numerator. Then our Y-intercepts, this also happens after reducing, which means it's happening after finding point discontinuity. And the way we find Y-intercepts, and we have forever, is to substitute 0 in for x and solve for y, which is the same thing as finding f of 0. Okay, so those should be no big shocks on how to find them, but the order in which you do it is super important. Depending on the function, you could get the total wrong information if you don't do it in the right order. Of course, sometimes you get lucky depending on the function and it might not matter, but you might not know at the beginning. So let's start by finding the domain. So again, yes, it's the first step, but to get to the first step, we have to factor. So let's factor this. We'll have f of x equals x minus 2 over, what is this right here? It is a difference of squares, x plus 2 times x minus 2. Okay, so I can reduce. I see that, but I'm not going to. All I have to find right here is the domain, all right? So I know that x cannot equal 2, right? And it cannot equal negative 2. So I could write this as interval notation, but I can also use set notation, and that makes it a little bit easier to write. So if I write it in set notation, it would look like this. The domain is the set of all x's such that x cannot equal negative 2 and x cannot equal 2. Now, I told you when we started writing them like that we were cheating a tiny bit. I was letting you not write a part of it. And I want to point that out to you right now because in Delta Math, when you choose how you want, you can choose how you want to give your answer. Whether you do it in interval notation, which is fine, just don't forget the union symbols, or you can do it or it says all values except for 1 or all values except for 2. So it pops this notation up for you and you just fill it in, but it has that extra piece that I've let you leave out just because there's so much writing. And so although I would be okay with you writing this, just so you know that it's not anything else weird. The official way to really write this is the set of all x's such that x is an element, it's a weird looking E, of the real numbers, and then x cannot equal -2, and x cannot equal 2. Okay, so it's this part right here that we've been leaving out and just saying, okay, we're just going to say that they're all real numbers that we're dealing with right now. But that's the official way to write it. So set notation sometimes is not all that much easier than interval notation, but that's what it'll look like. So basically, it would pop all this stuff up that I've underlined in pink, and then you just have to fill in this part right here. Okay, but you can do it in interval notation, like I said, or whatever. Just look at the little drop-down menu for your options. Okay, so let's look at number 2. So the first thing I'd want to do is factor. Well, don't need to factor, right? Nothing I can factor there. And I'm looking for the domain. Sorry. Looking for the domain. So the zeros of the numerator don't matter. I don't have any holes. The only thing that's going to affect my domain are the holes in the vertical asymptotes. So I have this right here. So for my domain, it's a set of all x's such that x cannot equal -11. There's really no work there to get my domain. All right, let's look at number 3. So I have 2 differences of squares. So I'm going to factor. So f of x equals x plus 3 times x minus 3 over x plus 5 times x minus 5. All right, and so again, the zeros in the numerator don't matter. I don't have anything I can cancel out, so there's no holes, but I have 2 asymptotes, so my domain is a set of all x's such that x cannot equal -5 and x cannot equal 5. So there's your domain. Let's talk zeros. But I'm actually going to change this. I used to have X-intercepts and then I changed it to zeros, but I'm going to change it back to X-intercepts because that is what Delta Math is asking for. And it's very clear about it. It even says, give the X-intercepts in coordinate as a coordinate point. And that's what, when it's zeros, I can give set notation. When it's X-intercepts, they're supposed to be ordered pairs. So. All right, excuse me. Let's see, we're going to first factor this. So I'll get f of x is equal to x plus 2 in the numerator. The denominator I'm going to factor. Okay, so my signs will be opposite. I'll have a plus and a minus. It's going to be plus 4 and minus 2. So I do not have any holes, because if I did, I would need to take care of that right now. But I do have to find my zeros or my x-intercepts. They are the zeros of the numerator. So that means x equals -2. So my x-intercepts is going to be -2, 0. All right. So then number 2. Let's factor. This is g of x. In the numerator, I'm going to factor. So this gives me x and x. The signs are opposite. So this is going to be a -5 and a +4. Then I have difference of squares again. All right. So I can reduce this. So since I can reduce it, that means, so this x plus 4 and x plus 4, when I cancel that out, that means I have a hole. So my point discontinuity has an x value of -4. I know this question doesn't ask for it, but anytime it pops up, we don't want to just ignore it. We don't just get to cancel it out and move on. Then we'll figure out our y value here in just a second. I'm also going to need my x-intercept. So I get g of x equals x minus 5 over x minus 4. Okay? Because the function is actually this and this together. Like, you can't just say it's this part. It's this plus that, basically. So when I substitute in my negative 4, I'll get negative 4 minus 5 over negative 4 minus 4. So that's negative 9 over negative 8. So that's just a positive 9/8. Okay, so like this whole thing right here represents my function. Then to get my x-intercept, that is the zeros of the numerator. So it's going to be 5, 0. All right, let's look at number 3. There's nothing to factor. There's nothing to cancel out. I just have f of x equals 5 over x minus 3. So since my x-intercepts are the zeros of my numerator, I don't have any. If I set 5 equal to 0, like, that doesn't even make any sense, right? There's no variables up here, which means I don't have an x-intercept. So I do not put none if I am using set notation. Now, this asks for intercepts, but we'll talk zeros in just a second. So for my x-intercept, we're going to say none. There will be a choice in Delta Math that you choose that says there are no x-intercepts. But let's talk set notation. What if I was asking you for zeros? Okay? If I was asking you for zeros, then I don't put none. Okay? What I would put is, what we normally do in set notation for zeros is we use these little brackets, right? Well, if there's nothing to put in it, then there's nothing to put in it. And it looks like that. Okay? So that's what you would do. That is called the empty set. So let's write this down. This is the empty set because this is something we need to know. The empty set looks like this. It's literally a set that's empty. Or it could be this circle with a line through it. So at this point, because I haven't seen as much of your work as I would at this point in the year, there would probably be at least one student, probably more, that writes their zeros like that I would have to say, look, you're not saying what you think you're saying, so just because you want to make your zeros pretty and cute, that's not a zero. That's an empty set, and it means something else. Okay? And then, so if you write your zeros like that, that's got to stop mathematically because you're saying something completely different. The other thing that you don't do is you wouldn't put an empty set with the empty set in it because that's an empty set that represents an empty set. So that's a big fat no. All right. So again, in Delta Math, they're not asking you for empty set. They're not asking you for set notation. They're asking you for x-intercepts. So you would just choose that there aren't any. But we're going to talk more about set notation, and actually this is something you need to be able to actually use and understand. All right, let's look at number 4. So I'm going to factor g of x equals, so numerator, x and x, this is negative, so they're opposite. And then my numbers would be negative 4 and positive 2. Then I would factor down here, so I get x plus 3, x minus 3. And nothing cancels out, so I don't have any point discontinuities. So I can just find my x-intercepts. There's going to be 2 of them. I'm going to have negative 2, 0, and 4, 0. So now let's talk y-intercepts. I probably should have boxed this one. This is my actual answer here. All right, my y-intercepts. So really, to find my y-intercepts, it is just f of 0. So if I want to find f of 0, those are going to 0 out, this, that, and that. So that's 0 minus 3 over 0 plus 11. So that's my answer, basically. I just have to write it as an ordered pair. My y-intercept, think about what is your x value. Our x value is 0. Our y value is negative 3/11. So normally we're not finding the y-intercept all by itself, but remember that's something else we do after all of the rest of everything. So I will have already factored, so let's factor this. F of x is equal to, I have a difference of squares, x plus 3 times x minus 3 all over x plus 3. So that means I'm going to be able to cancel something out. So I am going to have a hole. So I'll have point discontinuity when x is negative 3. So then those are going to cancel out. So I have f of x equals x minus 3. So to find my y value here, that'll be a negative 6. And then to find my y-intercept, I find f of 0. So that means I'd get 0, negative 3. You may think, oh, I could have found that without canceling it out and everything, but sometimes there's x's that you cancel out that affect your y-intercept, so trust me, and you do it after you do all of that other stuff. Okay, number 3, nothing to factor. So if I find g of 0, that's going to give me 1 over 0 squared. Well, can't have that, right? So that's undefined. It's not an empty set, because first of all, a y-intercept is not a set. Not an empty set because it's undefined. It's not that there's nothing there. We do have something, it's just undefined, which means I do not have a y-intercept, so that would be none. All right, then last one. So we need to try and factor to see if we can cancel out any point discontinuities we might have. And if I look at the numerator here, I would need two numbers that multiply to give me 11. My only options there are 1 and 11. And they'd have to combine to give me 3. That does not exist. So that means that I cannot factor the numerator. If I can't factor the numerator, don't even care if I can factor the denominator, because I won't have anything I can reduce. So then I just need to find g of 0. So remember, when you're doing that and you have this all, I don't have to actually like substitute it in, because think about what happens. When I substitute 0 in there, it zeroes out. 0 in there, it zeroes out. That zeroes out, that zeroes out. I'm just left with that part right there. So that's 11 over negative 4. Then, of course, I would reduce if I could. And then my y-intercept is just going to be 0, negative 11 fourths. Okay. There you go. And hopefully those are things that you can take care of so that we can move on to start graphing these rationals.